So it's a pleasure to have Masha Baryakhtar here from the University of Washington, and she will talk about new particle searches with gravitational waves. Thanks.
Thank you. Hi, everyone. It's really exciting to be at GGI, although unfortunately not in person. I always love being there. Thanks for organizing the fun workshop. Unfortunately, it's just starting to get late here, so I haven't been able to make most of it. But, so today I want to talk about a few ideas for new particle searches with gravitational waves. And of course, we just heard a whole talk about various kinds of stochastic backgrounds. So I'm focusing on possibilities for searches in the local universe. And the question I want to bring up, and I know there'll be discussion later, is how do we use observations with current and near future observatories, which are very exciting these days, to look for beyond the standard model physics, in particular with a focus on particle physics parameter space. So one of those kinds of parameter space that's a favorite of mine is ultralight axions. And I think for this audience, I don't need to go into the details of the motivation for axions, but the highlights are that these very light particles are solutions to one of these outstanding theoretical puzzles that we have in the standard model of symmetries, which is called the strong CP problem. This is particular to the QCD axion, which is shown in this green line on this plot. I don't know if you can see my mouse, but there's a green line on the plot, and
we can see it. Thanks.
Okay, great. And then there's signatures also of high scale physics, because as you can see, the couplings that are still allowed are quite a bit higher than any kinds of energies we can reach on Earth. So just the discovery of an axion would immediately tell us about physics at scales that we'll never be able to reach in a collider. And they're also really elegant candidates for dark matter of the universe, whether or not they solve the strong CP problem or not. And I just wanted to point out a few examples today of how you can look for these with gravitational waves. And so I'll briefly talk about searches for fuzzy dark matter, which is actually off this plot, but I was too lazy to extend it to lower masses. So there's fuzzy dark matter at very low masses, which could be ultralight axions of 10 to the minus 22 EV. There are also constraints from neutron star forces for axions above this QCD axion line. And then there are searches for black hole superradiance, which probe axions or any other gravitationally or very weakly coupled particles in the range of wavelengths that correspond to black hole sizes. So Pulsar timing array searches for fuzzy dark matter. I refer you to the next talk for details on how these details about the Pulsar timing array experiments. And I just want to mention here that the millisecond pulsars that are observed, they form a galaxy-wide network of very precise clocks, which enable searches for basically changes in the metric due to gravitational waves or due to dark matter oscillations. And in particular, in 2013, there was the proposal that ultralight dark matter can cause changes in fluctuations of the metric in our galaxy, which may be observable by Khmelnytsky and Rubakov. And the idea is very simple. You have a scalar field with mass m, and normally we calculate the energy density. We all know it's 1/2 m squared phi squared. And then if you go to higher orders in the velocity, which shows up in this momentum here, then you see that the energy density locally has an oscillating piece, but that's suppressed by very small dark matter velocity squared. But what they found was that there's a pressure term which oscillates on frequencies of twice the mass, and it has a large amplitude. Normally, we don't think about this because it averages out very quickly, but it can result in metric oscillations that can be searched for with this clock network in a slightly different analysis than what you would do for gravitational waves, but you can get the same kinds of overall sensitivities. So there's these results, which I'm not sure if it's the latest, but that's the ones I know of from 2018, where you can place bounds on the energy density of dark matter in this fuzzy regime, where fuzzy just refers to the fact that the mass is very, very light, and as a function of the boson mass. So the current bounds are shown in black, and then future projections are shown in purple. And the horizontal lines are kind of targets for what the energy density is at various places in our galaxy. So you can see right now the bounds are not really reaching the target density, but and furthermore, these are kind of at the frequencies where there's already many other constraints on this type of dark matter. But I think this is a very, elegant signature where you have this dark matter particle, and you can, without any further assumptions, you can search for it using gravitational wave techniques. So that's why I wanted to highlight it here. Thanks, Kira. The second point I wanted to highlight is neutron star searches for axions. And here, the idea is that the lighter than expected axion, and I'll explain what I mean by that on the next slide, can mediate forces between neutron stars that can be as strong as gravity and change their in-spiral waveforms. And so if we go back to my axion plot here, where on the y-axis, I really mean FA, which is this QCD coupling of the axion, the one that's set by the coupling to GG dual. What we expect here is really a line. There's no kind of band that you typically see in the, for example, photon searches. But to get to this line, you need to go through all this other parameter space. So it's worth thinking about experimentally. If you want to get to this line, you need to go through all this empty parameter space here. And so it's worth thinking about what other constraints there can be on these types of models. And these are axions that are lighter than you would expect from the QCD contribution. So I'm calling them tuned mass axions, where you have to cancel off some of the contribution of the QCD potential. So this was studied in a paper by Anson and Junwoo, where the tuned mass potential is just taking the regular contribution to the axion potential, but then sticking in a small parameter. And they have a few examples of toy models of how to do that. And so this epsilon here is a small number, which lets you go to the left of the QCD axion line. But then what they pointed out is that if you have a finite density correction, that typically gives another contribution to this potential, which is normally not something we think about because it never really dominates the vacuum contribution, at least in places where we can calculate it. But if the vacuum contribution is suppressed, then the finite density corrections can flip the sign of the potential. So there's a relative minus sign between the vacuum contribution and this thing proportional to the density of the nuclei, and move the minimum of the potential away from where we usually think of it at A equals 0. So what this does is the potential energy, which is proportional to this potential term that I just showed here, is minimized if the axion values of order pi f inside matter, whereas the gradient energy of the axion, of course, is minimized if the axion value is always the same, if it remains 0. But if your object is very large and dense, for example, a neutron star, then even though you can have a very large gradient energy, you still win if the axion value flips inside the object. So this is not the actual axion profile, but it's kind of a cartoon of what you would see. If you have two neutron stars, there's different examples of what the axion field would look like as a function of radius. So inside the neutron star, the axion would be at f pi, or it could be at minus f pi. And then outside the neutron star, it would be at 0. And then you'd have this profile that's sourced by the outside of the neutron star that extrapolates between the two. And if you have these profiles, then this would give rise to scalar radiation of these axions, as well as additional forces between the neutron stars that change the in-spiral dynamics, because the axion field gradients will cause the neutron stars to come closer together even faster to relax the gradients, or if the sign is different, it'll push them further apart. So you expect on length scales, when the neutron stars are separated by less than the Compton wavelength of the axion, you expect them to start, you expect this effect to start affecting the in-spiral. And this was done in LIGO data in searches for we're using GW170817, which is the first neutron star merger that they saw on my birthday 4 years ago. And they had these nice results by this group down here. So this parameter space is a zoom in on what I was showing before. The QCD axion line is on the bottom right. Then there's other constraints which were worked out previously as well. For example, from Big Bang nucleosynthesis and the sun, if you have these types of potentials, you can get other interesting effects, which would exclude this parameter space. And then if you have these neutron star in spirals for axions of order, neutron star sizes and lighter, you can constrain this parameter space from the fact that the neutron stars spiraled in as we expected them to in general relativity. Finally, I will talk about black hole superradiance, which is a lot of it is my own work. So I'll go into a bit more detail. So these are searches for ultralight particles where you can use the fact that rotating black holes produce clouds of weakly coupled bosons through a process called superradiance, where they extract the energy and angular momentum of a black hole, placing it into these bound states that we sometimes refer to as gravitational atoms, allowing tests of ultralight and ultraweakly interacting bosons. So a lightning review is that for a massive boson, the gravitational potential barrier, just the G M black hole M axion over R squared force can provide trapping, which gives these bound states, and the ones that satisfy the superradiance condition, which means that they rotate slowly, the phase velocity is slow compared to the angular velocity of the black hole, will grow exponentially by extracting energy and angular momentum from the black hole and converting it into more and more axions. And the rate of this process is fastest when the Compton wavelength of the axion is slightly larger, but still comparable to the black hole radius, so that these atoms bound states sit kind of outside, but still close to the black hole, so they can have a significant overlap with the horizon and extract energy efficiently. And the play-by-play of this process is that if you have a rapidly rotating black hole that's formed, for example, here, so on the left-hand plot with the blue, I'm showing a black hole spin from 0 to 1, where 1 is an extremal black hole that can't rotate any faster. And then the x-axis is the black hole mass. If it starts up here, say in a merger or supernova that left it with a large natal spin, in about a year, if we have an axion with mass 6 times 10 to minus 13 electron volts, it'll drop down. The angular momentum will drop down by almost an order of 1 factor. And in the meantime, the number of axions outside of bound to the black hole will grow, as shown on the right-hand side. So the growth is exponential, and then it saturates once the black hole reaches this line, which is the superradiance condition, where the velocity of the axions matches the velocity of the black hole horizon. And so you can see the black hole spin drops by a large amount in the last e-fold of this evolution. So this process will then continue, where the next step in the evolution will occur, because there's different kinds of bound levels, and the ones that are localized further away can more easily satisfy the superradiance condition, but the growth rates are parametrically longer because their overlap with the black hole is smaller due to the larger angular momentum barrier. So you can see this next level, which I've called 322, is growing on now million-year time scales, but kind of repeats the same story. The black hole again drops in spin. And in between, the first level actually depletes over time on parametrically longer time scales than the growth. And this is due to the fact that these axions are sourcing gravitational waves, and that's reducing the energy in the cloud. So this presents us with 2 classes of signatures. First, you have gravitational wave emission, as I just mentioned. So the gravitation, just like the fuzzy dark matter case, the energy density in the cloud has an oscillating component, and that oscillating component at twice the mass of the axion, or more precisely twice the energy of the axion, will source gravitational wave radiation at exactly that frequency. So it'll be a very coherent gravitational wave that you can search for. And the other signature is that you have black holes that spin down. So if you see a black hole that's rapidly rotating, or you see particular patterns in the spin mass plane, you can reach some conclusions about whether these particles exist or not. So for the gravitational wave signals, what you should be picturing in your mind in the source frame of the signal, so if you're sitting on top of the black hole, is that the strain as a function of time is a very simple cosine function, which is just oscillating at twice the energy of the axion, and it's slowly decaying over time in amplitude on time scales that are between days and billions of years, as the cloud slowly depletes from these axion, what we call annihilations. And we and other groups have found that we can have up to thousands of signals in our own galaxy from these types of gravitational atoms, if you look for these coherent gravitational waves. You can also, if you have that many signals, you can also instead look for excess power in a narrow frequency band. So look for a stochastic gravitational wave search. Or you can do follow-ups to mergers. These are the most exciting in my mind because these are the least affected by astrophysical uncertainties. So the idea is you have a merger. Those tend to give you very rapidly rotating black holes because you capture all of the angular, or a large amount of the angular momentum of the binary, as well as any contribution from the initial spins of the 2 black holes. So you end up with a typically quickly rotating black hole. You know roughly where it is, on the sky, and you know its mass pretty well, and you know its spin pretty well, and you know its distance okay. So you can do a search specifically pointing toward that black hole and seeing if there's a follow-up signal afterwards from these axions around the black hole that are sourcing gravitational waves. So these are have been studied by us and some folks affiliated with LIGO, and now we are not sensitive enough because these mergers are so far away, but I think this is an exciting thing to keep in mind for future iterations of gravitational wave detectors in that band. So focusing on the current searches, you can look for, as I mentioned, these monochromatic signals. So on this plot, I'm showing the number of detectable signals as a function of axion mass. Each of the dots is showing how many signals you would see if the axion was at the mass specified on the x-axis. And there's different scenarios assumed here for the black hole distribution, because of course, in order to get superradiance, you need the black holes to be initially quickly rotating. So those are the circle dots here, which give you the highest rates. That's if we assume that the black holes in our galaxy have a flat spin distribution between 0 and 1. So a significant fraction of them is rotating pretty quickly. If, on the other hand, you look at the triangle points where you say none of the black holes are ever born with spin less than a third of its maximal spin, then you only get a handful of events down here, and then the squares are in the middle. And there's also differences depending on which black hole mass distribution we assume, although that's a smaller effect, which kind of changes a bit the shape at lower axion masses. Most of the shape of this curve is specified also by the LIGO Virgo sensitivity. So this is with actual data that looked at these continuous wave searches in the 01 run. There's also other results for more recent data, and we don't see any axions. So in principle, we don't see any of these signals. So in principle, we could exclude most of this mass range, but of course it has very large astrophysical uncertainties. So we don't quote a specific exclusion. But if you take reasonable black hole distributions, you could disfavor axions around 10 to the minus 12 EV in mass. And what I want to highlight is that, well, first, if you see searches of gravitational waves that are looking for axion or boson superradiance, you should always ask what distribution of black holes they're assuming. And the other point is that I think it's also very exciting here to go to high frequency. We heard this a bit in the previous talk as well, that there's not as many searches going on at frequencies above the LIGO Virgo band right now. And if you go to higher frequency, you could go to heavier axion masses, which would get closer to, say, axions with a gut decay scale F. Of course, at some point you run out of black holes that are the right size, but there's still a bit of room for improvement at these higher frequencies. And finally, you can also use LIGO to look at black hole spins. So we have measurements of rapidly rotating black holes that can constrain parameter space. So this is the same plot as I was showing before in blue. We have the black hole spin on the y-axis and the black hole mass on the x-axis. But now we assume some idealized black hole distribution of initial black hole spins as they're born, and then they spin down to these superradiance condition lines. So you can see that you don't expect to find any black holes in the upper right corner of this plot if there's an axion mass of 6 times 10 to minus 13 eV. Now, of course, specifically the initial black holes at LIGO, their spin is not very well constrained. It's not a leading effect in the waveform, but so you need a lot of statistics to get something that looks like this. But fortunately, we are starting to get a lot of statistics. And there's not a lot of evidence. There's no evidence right now for bosons in the first two runs, first two data sets from LIGO Virgo. But you do get a result, which is that there's two events which had initially rapidly spinning black holes that would fall into this white region here, and they exclude this factor of 2 in axion mass. And this was an analysis done by these folks here, Ken and Savo et al. So they did a full statistical analysis of all the black hole mergers to that date. So this is the first LIGO black hole spin exclusion, which is very exciting. And in the future, perhaps you could also see some hints once you get enough black holes to see an interesting distribution. So let me wrap up. I talked about a few ideas in the general theme was axion or ultralight boson particles. So you can look for very light fuzzy dark matter with pulsar timing array searches analogous to gravitational wave searches. You can also look for tuned mass axions with binary inspirals of neutron stars. And you can look for ultralight axions. I didn't focus on this, but you can also look for other bosons or like spin 1 particles using black hole superradiance. And that gives you 2 types of signatures to look for gravitational wave detectors. One is the lack of highly spinning black holes, and the other is continuous and stochastic gravitational waves that are emitted by these gravitational atoms. And what I find really exciting about these sets of searches is that you start with a particle that's well motivated already. Well, maybe the tuned mass axion we can argue about, but you start with a parameter space that's very well motivated from the particle physics point of view, and then you can put bounds on that parameter space using new effects and searches using gravitational wave physics. So I'd love to hear more ideas about how we can populate this parameter space with other types of gravitational wave searches for beyond the standard model particles and connect that back to kind of our fundamental physics understanding of what those particles are and why we'd like to see them discovered. So thanks very much. That's it.
Thank you very much, Masha. Are there any questions? I see a comment, but I think you read it as you were speaking, right? So
yes,
you can repeat it for the people in presence. Yeah, okay. So this was referring to the pulsar timing array results at the beginning of the talk. So yeah, I see a question from David.
Oh, hey, Masha, it's David. Thanks for the nice talk. I like this closing slide because I think there's people that study exotic compact objects. I mean, you know all about this, where they literally want to consider not just things like black holes or stellar relics that are sort of contaminated with new particles, but literally just globs of new. Hello? Oh, like scalar
yes.
field stars or things, boson stars or things like this. And in that case, we did some studies on dark QCD mirror stars, and a few others have done this too. And in that case, you end up essentially filling this plot in a very indirect way, where where you're measuring some dark exotic compact object mass function and the deviations in the compact object from the black hole tell you something about the equation of state. So maybe you can build up some other, you can measure some combination of coupling and masses that way. So it's all kind of quite oblique and depends on the dynamics of each particle very sensitively, but it's kind of insane that if there is anywhere in the universe a few of these, then, you know, in 10, 20 years, we should see something that really looks very, very different. So there's going to be a lot of ways of filling this really cool plot. So it's just a comment, but thank you.
Yeah, thank you. Yeah, exactly. I think it's, you know, there's a lot of exciting ideas, and I think it's really nice to, you know, like you said, there's a few steps to go in between the, you know, the particle physics and the final waveform that you'd see. And I think it'll be also very interesting to, you know, to the extent that we can, to try to make that connection more robust to be able to fill out this plot. And I know that's, you know, I know your people are thinking about that, but I just want to emphasize it.
Yeah, I also have a kind of a naive question. So if you go back to the exclusion that you showed on the axion from Neutron star in space.
Yeah, you're cutting out a bit, but I think you said the neutrons start in spirals. I can't, oops, sorry. I don't know what I did.
Yeah, I think we lost your slides.
Reshare the screen. 1 sec, there you go. Share, okay. Yeah, here it is.
Yeah, so my question is a bit vague. I just wanted to know if, I mean, there are some assumption in this exclusion, like, I don't know, some parameters of the merger are degenerate with having an axion, or if the measurements that you have are enough to pin down all the characteristics of the merger and the axion.
Yeah, that's a good question. I don't know the details, but so what I do know is that, so each of these points here was a, you know, specific search for these axion parameters. And then they said, well, if you have an axion that's much lighter than that, then, you know, for starting here and going to the left, it's going to be the same effect because the wavelength is long enough that you don't see it in the first place, the effect of the finite wavelength, so they can extrapolate to these very light masses. Of course, the assumptions are that it makes sense to have this type of potential in the first place, which is why there's this gap between the QCD axion line and this exclusion, so that the tuned potential is fairly small compared to what you would expect. And that gives you some perturbative control of this effect. But as far as I understand, they do, you know, full expansion and do fits to these specific points, and then there's extrapolation to lighter masses.
Thank you very much. I see a question from Zoom. So Liang, please unmute yourself.
Hello, Masha. Thanks very much for the nice summary on this topic. I'm wondering, apart from those black holes detected by LIGO Virgo, what about other black holes in the universe? For example, you know, these black holes discovered in X-ray binaries, or the very massive black holes at the centers of galaxies. So will they be used for superradiance constraint?
Absolutely. I didn't discuss it just for lack of time, but yes. So this is the constraints that you can get from X-ray binaries that you mentioned. So these are black holes that have stars orbiting around them. So they have an accretion disk that's the star being dragged around the black hole. And you have the spins of these 5 guys up here have been measured. And so we use that to place exclusion in this mass coupling plane. For your reference, the LIGO one I mentioned is in purple here. They didn't do an analysis that's a function of F. So that's kind of a cartoon here. But the gray regions are the ones that are excluded, and the blue bands are kind of the errors from the spin and the mass of the black hole. And you can see the QCD axion line is here, and there's a ALP dark matter line here. And the bounds get weaker at large F, which I didn't mention. But if you have strong self-interactions in the axions in the cloud, you have a depletion of energy from the cloud, and that can slow down the spin extraction. And so that's something we worked out with Robert, Marius, and Olivier in this paper. So absolutely, you can place interesting constraints. For supermassive black holes, you can do the same kinds of analysis. We didn't focus so much on that because there's, I think, a lot of theory work to be done to understand the evolution of the black holes and how that affects the superradiance. So for these black holes, it's kind of a clean system. At some point, black hole was formed, and then there was this binary. If the axion is too light, the cloud is too fuzzy, and it could get disruption or some resonance effect with the orbiting star, which is why we cut off the bounds on the left-hand side here. But for supermassive black holes, kind of by definition, they form through accretion and mergers, which are quite messy events. And there's some interesting work that's being done to understand how perturbations affect the cloud, but it's hard to translate that into robust exclusions at this point, I would say.
I see. Thanks. And also from this plot, it seems that this parameter space of dark matter being axion-like very light particle is ruled out by the X-ray binaries. Is that?
Yeah. So yes. So if you have this, so this dark band is order 1 axion misalignment, and then you can tune to the bottom of the potential or to the top of the potential, which is the slider band. So of course you can keep tuning to fill the whole parameter space, but then you might get other signatures as well, especially if you tune to the top. But yeah, so this is very constrained. And I also didn't emphasize, I just want to say here that axion superradiance doesn't depend on the dark matter density, which is another thing that I find, that's particularly special about this type of searches. So you just look for the particle existing in the Lagrangian of the universe. Yeah.
I have another question related to these galactic potential sources of black hole superradiance. So you mentioned that the estimate is that perhaps there's order 1,000 detectable sources, and here detectable means that, for example, these are detectable with a proper matched filter search, or they are detectable with some incoherent searches. Because the reason I ask is because I think, as far as I know, the full matched filter search for such extremely long-lasting quasi-monochromatic signal is computationally very expensive. And currently, yes, what is being done at LIGO Virgo is, I think it's some method that sits in between fully coherent search and the fully incoherent search. So how are these detectability calculated?
Yes, so exactly. So these searches, so as I mentioned, in the frame of the black hole, it looks like a very clean monochromatic signal with maybe a very slowly decaying envelope. But as you say, in reality, these are very difficult to search for at LIGO because, if you're doing a blind search, you don't know where the black hole is. Most of these black holes we will never observe. And that has relative motion to the gravitational wave detectors. So that creates a lot of extra parameters in this waveform that you would see on Earth. And basically they just scan over all of those, and it becomes computationally very expensive to do that, to add that data in a coherent way. So they break up the data stream into chunks and analyze each one coherently and then add them incoherently. And so that's exactly the search that we're quoting here. So we worked with the people, Maria Alessandra Papa is one of the leaders of these searches at Hanover. And so these are results from exactly those searches. And it would be great if there are, interesting methods to do better. I know they've been playing with different other algorithms to do these searches that make different assumptions. But roughly the sensitivity is within a factor of a couple of what I'm showing here. So these are the number of detectable signals that you would have seen in current analyses that have been done with data that's on tape, with these kind of continuous wave searches is what they're called. You could also look for stochastic searches where you just incoherently add up this power and look for excess power in this bin, and that's what's been done by these groups here.
So
Does
I
that
guess
answer your question?
That's a very detailed answer. And I guess for the loudest signals, if we don't see those signals with the suboptimal search, then it is still a valid constraint on the parameter space, right? So that means, I guess, am I correct that either this particle doesn't live in this part of the parameter space, or maybe the potential number of sources is much less than the estimate, so that maybe the nearest detectable source is actually pretty far, and then you need a improve the search to improve sensitivity, right?
Yeah, exactly. So there's a couple of issues that we studied in this work, which is that, these searches, these continuous wave searches were designed not to look for axions, but to look for neutron stars that are not perfectly axisymmetric and emit some gravitational wave radiation, but with a similar type of, monochromatic signal. And so those searches were kind of tailored to looking for just one signal in this whole frequency band. Where here you expect many, many signals that are clustered together within a fairly narrow frequency band because it's the frequency specified by the energy of the axion, which is of order of twice the mass of the axion with a small spread because of Doppler shifts and because of binding energies. So we are a bit worried that if you have many of these clustered together, some of the pipelines would throw it out as noise, or would over subtract the noise background if they're averaging over nearby frequencies. So we did look at that, and that could be an issue here, but people they looked more closely at the data, and you would have basically seen by eye if there's something happening of that nature. So what you're saying is correct, but it was slightly non-trivial to get there. You have to be a bit careful.
Thanks very much for your answer.
Yeah, thank you.
Okay, let's thank Masha again. And